you. First of all, I thank the organizers for this nice conference. Yeah, my name is Kishan Deka, and I'm going to talk about the impact of galactic foregrounds in the lensing reconstruction and the lensing of CMB B modes, and eventually I will also show the impact on the tensor to scalar ratio constraints. So my advisor is Paweł Wielewicz, and I work at the National Center for Nuclear Research in Warsaw, in Poland. Okay, let's start. So I'll start with this beautiful picture of evolution of the universe. For my work, what I am interested mostly in is what's happening in this region and what's happening to the CMB photons when they reach us. So first of all, let's focus here. So this is the inflationary epoch where the quantum fluctuations got amplified due to inflation. And the inflationary models predict some tensor fluctuations, tensor modes, which are created by the primordial gravitational waves. And these fluctuations are imprinted on the CMB photons, and we can see it in the CMB polarization, which is also called tensor B modes. So it's a B mode polarization pattern that comes from these primordial gravitational waves. And if we could detect this signal, this CLBB primordial, then we will be confirming the inflationary gravitational waves, the primordial gravitational waves. So this is basically the goal of next decade's CMB experiments. And my whole work is based on constraining the amplitude of primordial gravitational waves in terms of this next generation CMB experiments. So what are these B modes? So these are the signal that is imprinted on CMB due to this piece of PZW. And if we want to constrain them, we want to probe this parameter, which is called R. And it is defined as the ratio of amplitude of the tensor fluctuations divided by the amplitude of the scalar fluctuations. So this is the quantity that we want to constrain. And right now, we have constraint from Planck and Bicep survey, and the tighter constraint is 0.032, but the next generation survey, they want to constrain it up to 0.003. Again, coming back to this picture, so we know that the CMB photons decoupled from the matter, and then it traveled to us to the point where we can see it today. And while traveling through this dark matter distribution of the universe, the photons experience something called gravitational lensing, right? That's very easily understood. And this lensing is very weak. So the impact of the lensing on CMB map is very weak. That's why it's called CMB weak lensing. And it is quantified, this lensing is quantified by this field, which is called lensing potential field, and it is basically defined as the integrated effect of the lensing of CMB photons by the gravitational potential that is on the way from the last scattering surface to us, right? And the way the lensing impacts the CMB is that it remaps the primordial anisotropies, and it basically remaps these anisotropies in some different direction when we observe it today. And this remapping is given like this as a gradient of the lensing potential field. Okay. This lensing potential field has been reconstructed by the previous surveys. For example, the Planck survey tried to probe this lensing potential field, and they got somewhat a noisy estimate of this field. And this field can be characterized nicely by a power spectrum shown here. And you can see that this power spectrum peaks at around 100 multiple, which is like around degree scale on the sky. And also this weak lensing effect is maximum at around redshift 2. So if we can reconstruct this field, we can actually also understand the mass distribution in between the last scattering surface and us, right? Now, coming back to B modes, so why this lensing field is important is because this lensing can also introduce some new polarization patterns that is produced by twisting the primordial E mode pattern. So we have this E mode polarization pattern, which are generated by scalar fluctuations, and we have B mode polarization patterns, which are generated by tensor fluctuations. But lensing can also twist this E mode pattern and generate some lensing B mode. And this lensing B modes will basically contaminate our observation of the tensor B modes. So here is the plot that I show you basically to show the amplitude of this lensed B mode. So if we want to probe, let's say, the tensor B modes of R equal to 0.001, then you can see that at all the multiples, it is mostly dominated by this lensed B signal, right? So if we want to constrain our R to this level, we must first subtract this lens signal so that we can get to this primordial tensor B mode signal, and then we put a constraint on R. So that's the motivation of this entire work, is basically do the lensing reconstruction of this deflection field, then subtract this lensed B modes, and then try to improve the constraints on the tensor to scalar ratio, which is R. And for this, there are some experiments already planned. So this CMB stage 4 survey is basically targeting these tensor B modes, and it will be targeting to achieve a constraint of 0.003. And the observation site will be at Atacama from Chile. There was another observation site in South Pole, but it was rejected. So if I compare the specifications of this new survey compared to, let's say, Planck survey, you can see here that it's a very huge jump in terms of angular resolution and also noise level. So it will be very good if we want to probe very weak signals. Okay, if we want to reconstruct this lensing field, we use some method called quadratic estimator. How this method works is basically we take CMB observation maps, we filter them in a certain way, and then combine them to get an estimate of the field. So how you can understand it basically is analogous to galaxy surveys. So in galaxy surveys, we observe the correlation in shapes and orientation, right? And from that, we derive the weak lensing effect. So similar in CMB as well. So we basically observe how these anisotropies are correlated within a local region, and then from that information, we can reconstruct the lensing potential field. We can reconstruct how much the CMB is lensed in that area. So this reconstruction method is a very local estimator. It will estimate locally from the observing the anisotropies nearby. And by doing it all across the sky, you can basically get a full sky map of the lensing estimate. But this lensing estimate is not completely noise-free, because it will have some noise from the reconstruction method itself. And this noise comes from the fact that we also have noise in the CMB maps, and there will be disconnected terms, Gaussian disconnected terms, which can contribute to the estimate itself, which is not a lensing signal, but just coming from noise. So that will contribute to this noise term, and the rest of the part will be signal. So how this noise looks like, if you want to see, is shown here for two different experiments. I'm comparing everything to Planck, basically. So for Planck kind of experiment, for Planck kind of noise levels, you expect some reconstruction noise at this level. And here in the black line, it's the signal that we want to probe, we want to reconstruct. And these are the noise levels for different estimators. So remember that we can combine maps. So we can combine temperature and polarization maps to get an estimate. So we can have different type of estimator of different combination of maps. That's why there are different estimators, and all these different estimators will have different noise associated with it. For example, for CMB S4, because CMB S4 is a very good, it has very good specification in polarization, That's why the polarization-based estimator works the best. It has the lowest noise, so it will have the highest signal-to-noise ratio. So this is the estimator that we are going to use in the future when we have data from CMB-S4 and also on the simulations. And this estimator is called EB estimator. It takes one E field and one B mode polarization field, and then from that, it estimates the lensing potential. Now, life is not that simple, right? So when we observe the CMB, we also have galactic emissions that's hindering our observations. So basically, we lie in the galactic plane, and the galactic emissions, dust emission from the thermal dust particles of galactic dust, and also synchrotron emission from the relativistic electron, they emit in the microwave range. So they will interfere with the CMB signal that we observe. And when we try to do this lensing reconstruction or delensing, it will impact our methods. So that's what I'm going to show, how it impacts. As I mentioned before, the reconstruction noise is also gets some impact from this galactic foregrounds, because this estimator basically tries to find the lensing signal from correlations, right? So this large scale or small scale emission from galaxy is also somehow correlated in between them. So from that, you will get an increase in the reconstruction noise if you have foreground. And if you don't have foreground, then you have very low noise in the reconstruction. So this is a problem that we need to solve. There's another problem that comes with the reconstruction when you have foreground, is that this reconstruction method is basically it doesn't know what signal is from lensing, what signal is from foregrounds. So sometimes the non-Gaussian signal present in the galactic foregrounds, it can misinterpret it as a lensing signal, and that will incorrectly estimate the lensing signal. So you can see here that this blue zigzag line is the signal that we reconstruct from our contaminated maps, and the theoretical sum of the signal plus noise is not as much as we recover from the simulated maps. But once we add this FL systematic bias, which we can compute analytically as well, given the foreground model, that if we can model the foregrounds, we can also compute this FL systematic bias. And if we add that bias, we see that it matches perfectly. But we don't want this. We don't want this systematic bias to be this big. So what we do is we want to do a component separation. So we want to remove the foreground signal by adding up multi-frequency observation from different frequency channels. So CMB-S4 will be observing in these different 7 frequency channels, right? So we can combine these different frequency maps because they have different foreground amplitude, foreground signal amplitude, but they have the same underlying CMB signal, right? So we can somehow make a weighted sum of these different maps so that the foreground signal galactic foreground signal is suppressed, but the CMB signal is preserved. And that's the constraint that we put on the weights as well. We put the sum of the weights should be 1 so that it preserves the CMB signal. But it can also vary in positive or negative values so that it negates the contribution from the foregrounds in different channels. And from a minimum variance method, we can actually get very nice cleaned maps that you see here. So here, HILC basically means harmonic internal linear combinations, which is, we do the same thing, this weighting thing, but we do it in harmonic space. We do it for different scales, different modes as well. So you have this, for example, you have CMB plus foreground for 95 gigahertz. We combine all these different frequency maps with a linear weighting, and then we get these clean maps, and we also have some foreground residue after the cleaning. Now the question is, does this foreground residue impacts our results in lensing reconstruction? So we tried to do the same thing after foreground cleaning, and we see that this FL systematic bias that I showed before is not present after we clean the maps and do the reconstruction again. So here you can see that this is the noise, this is the signal, and it perfectly adds up to the recovered signal from the simulations. So everything works fine here. The next thing is, once we get this reconstructed lensing field, what we want to do is create a lensed B mode template. So we create it from the observed E mode and the reconstructed phi. We combine them in a way so that it gives us a lensing estimate of the B mode. And then we can subtract this template from our observed B mode so that we reduce the lensed B mode effects, right? So this is called delensing of B modes. And for this to work nicely, what we need is a good reconstruction, which have high signal-to-noise ratio. And we need a E mode observation with less noise. And that's the goal of CMB S4. So this is basically the schematic. This is basically the idea of the sky coverage of this CMB S4 experiment. So what it will do is it has some large aperture telescopes which will observe this wide field shown in gray, light gray. So it will observe this southern part of the sky. From this observation, we'll get E and B mode polarization, and from that we can get this phi estimate here, this phi estimate. And then we will generate a template for this wide field, and then subtract that template from this small aperture telescope field, which will have high signal-to-noise ratio, and it will do a deep observation for this small field. Why there is like two setups is basically for the LEDs, we can go to high multiples, we can observe small scales. But for the small aperture telescopes, we cannot observe this high multiples. We just restrict our observations to the small multiples, so we observe large scales. Because when we do the reconstruction, we need this small scale information. That's why we will use the LEDs to reconstruct the field. And for the tensor mode estimation for the R constraint, we need this small scale, we need this small multiple information. And for that, we will use this small aperture telescopes. And this is how it looks for this deep field. We have the observed B mode. And this is the tensor component that is present in this B mode. We make a template for this small patch. We subtract the template from the observed B mode, and then we get a B mode called delensed B mode. And this will contain tensor modes. It will contain some residue from lensing. It will contain some foreground residue and also some noise residue. And if I combine all this information in a pipeline to give you an idea, this is how it looks. So we have, at the beginning, we have simulations of CMB plus foreground plus noise for these different channels. It goes into this harmonic ILC pipeline, which cleans the foreground signal. It will give you E and B map. From that, we combine this E and B map to generate this quadratic estimator, which will give you a phi estimate. And this lensing potential, the phi field, once we get this phi field, then we can generate, combining this phi field and this E field, we can generate a B template. And this B mode template then can be subtracted from this deep field observations of B modes. And once we get this delensed deep field B maps, we can do a likelihood analysis on them. And this is how the likelihood analysis looks like. So we have the model of the delensed spectra like this. The tensor to scalar ratio multiplied by the primordial signal plus lensing residue plus noise residue plus foreground residue. And if we try to constrain from here, if we do analysis on R, we get the constraint on R for these different cases that I show in this plot. So we do this analysis for 100 simulations. And in this plot, I show you the mean of R estimate from these 100 simulations and the error bars on the mean. So you can see that for the case of no foregrounds, here we have small sigma. But then these are the different foreground models that we used in our analysis. So these are in varying complexity. So this, for example, this low complexity doesn't have any non-Gaussian small scale added to it. But then we increase the complexity and we go to very high complexity where we basically add the non-Gaussian effects in the galactic emissions. And in the high complexity estimate, we see a small bias in the R estimate, and also the error bars increases. Now, to show you what contribution this different spectra, different terms have on the sigma of R, is basically we have the tensor signal, we have the noise residue, and all this combined, we have this sigma of R on the estimate of R. So you can see that it is still limited by this lensing residue. So we need to do better delensing. And for that, there are studies of iterative delensing method, which can reduce this lensing residue and tighten the constraint on R. And we're hopeful that we'll be able to achieve the goal of 0.003 for the CMB-S4. Yeah, in summary, we need to do lensing reconstruction to study these tensor modes. And we saw that foreground contamination is very interesting, so we need to remove them. And also, the constraint on R is still lensing limited, so we need to delens farther with some iterative methods. And also, accurate modeling of the non-Gaussianity that is present in the foreground, in the galactic foreground, is important to model it well, so that we can do our analysis on simulations, and from that we can get a better constraint. And then at the end, when we have data, we'll be ready to go. Thank you.
Thank you for a very nice talk. We have time for questions. Please.
So if you could come back to your 19, I think that was a nice slide.
Like here?
Yeah, you were talking about combining here a small field with very high signal to noise, with a low signal to noise, but with a very wide field.
The LEDs, yeah, this is wide field, but it will have high signal, high noise, yeah.
Yeah, so do you have some particular set of methods to use there? Or how are you planning to do that?
Can you repeat the question?
Like, how do you combine that? How do you have, like...
So there are different telescopes. For this large aperture telescopes, they will observe this wide field, and because of technical issues, we have high noise on this large scale, large aperture telescopes, because they also have like atmospheric noise component. And the small aperture telescopes, they will observe one patch for longer time. So they will do a deep observation. But this wide area, you have to watch it for less time because you need to cover more area, right? So it will have low signal to noise ratio.
Actually, this looks like a really good example of super resolution in deep learning application. Maybe you can have the high signal to noise from the small field of view, and then you can extract that information to other wide field. So you can make the wide field high signal to noise using super resolution techniques.
Well,
yeah.
I'm not sure about it, but the thing is, it's very convoluted because you are reconstructing this phi field from this wide area. So if you use any information from this small patch to reduce the noise and then try to reconstruct, then you might have some correlations. So we always try to have independent observations for this wide field and the small field. So there are no correlations because it's very convoluted way of delensing the maps.
Yeah, that's right. But I was asking, you might gain some extra information just because you know how it looks because they observe in the same patch, like overlap.
Yes.
But we can discuss it too.
Yeah, maybe we can discuss.
Is there any other question? Let me ask something. If I ask you to be very optimistic, what do you think is the best or the smallest scalar to tensor ratio we can hope to detect in the
So
future?
for now, the optimistic case is like we're targeting around 0.007, 0.01, around that. Yeah. From now, because
but
there.
Imagine your approach works out perfectly, and what coming from a theory side, if my model predicts a tensor to scalar ratio of 10 to the minus 3, is that something we can rule out?
10 to the minus 3, it's far down the line.
That's far down.
Yeah, but yeah, 0.01, it's possible. Yeah. Like if it starts observing, then maybe 5 years observations could be.
Okay.
Because there have been also there are 2 sites, but now the South Pole site is not, I think, funded or something. So basically, it's reduced.
Thank you.
Sure.
Let's thank the speaker again.